All right, let's work through this now, and then we'll talk about why it's important. Before we solve it with an inverse matrix, let's justify why it works, and we'll justify it in two ways, actually. One way we'll justify it is we'll think back to the definition of what it means to multiply a matrix times a vector that came up on exam 1, and I want to reemphasize it. And the other justification I'm going to give is a more abstract justification based on the equation AX equals B using matrices. So let's justify why we can first represent this system of equations as AX equals B. It's a system of equations. You're saying solve both equations simultaneously, find values of X and Y that solve both equations at the same time. Two scalar equations can be grouped into one vector equation. The equality of these two expressions is equivalent to one equality between vectors. The equality of the vector whose components are 2x plus 3y and 3x minus 5y with the vector whose components is negative 5, 6, right? Two equal signs there for the system of scalar equations, just one equal sign here for a single vector equation. These are equivalent to each other. The only way these two vectors are equal is if their components are both equal to each other. Then here on the left, we want to relate this to a matrix times a vector. The key way to do that is to break it into pieces. The first piece involving x, 2x and 3x, and the second piece involving y, 3y and negative 5y. Then for each of those vectors, factor out the scalar. This is the same as the scalar x times the constant vector 2, 3, plus the scalar y times the constant vector 3, negative 5. That's a linear combination of these two vectors, 2, 3, and 3, negative 5. That's the same as the definition of a matrix times a vector. What matrix? The matrix whose columns are 2, 3, and 3, negative 5, times what vector? The vector whose components are x and y. By definition, remember, back even before exam 1, of a matrix times a vector, we said you take a linear combination of the columns of the matrix, where the entries, the components of the vector, are the weights, the coefficients in front of those column vectors. That's what we've got here. That's the same thing as this. That's the same thing as this. So what we've got ultimately then is a matrix, call it A, a 2 by 2 matrix, times a column vector, a 2 by 1 vector. Well, of course, that is a matrix as well, but we're thinking of it as a vector, a two-dimensional vector in R2 equals this constant vector, call it B. In abstract form, then, this system of equations can be represented as AX equals B. Why can we use an inverse matrix to solve it? An inverse matrix of A, assuming it exists, has the property that when you multiply it times A, you get the identity matrix. The identity matrix, the 2 by 2 identity matrix, call it I sub 2, is 1, 0, 0, 1. That has the property that when you multiply it by a two-dimensional vector, you get that vector back. It acts like the number 1 for matrices and vectors. Just like the number 1 times any other number is that other number. 1 times 5 is 5. 1 times negative pi is negative pi. The identity matrix, this kind of matrix, acts like the number 1. If you take this equality of two vectors, this is an equality of two vectors, by the way. B is a vector, AX is a vector. Written as a column vector, it's this vector, really, right there. And you multiply it on the left by A inverse, assuming A inverse exists. Well, if these two things are equal, then these two things would have to be equal. I'm multiplying by the same thing on the left side of the equation. By the associative property, I can move the parentheses here. I can write this as A inverse times A times X. That's the associative property. Think of the associative property as allowing you to move parentheses because you're associating things in different ways. But A inverse times A, if A inverse exists, is this 2 by 2 identity matrix. That's the same as I sub 2 times X. The 2 just means it's 2 by 2. But again, I sub 2 times X, I acts like the number 1. You multiply it times the vector X, you get X. So what we've got here ultimately is that the solution vector X, if A inverse exists, must be A inverse times B. There's an abstract justification for why using an inverse matrix will solve the system. Okay. So you've got to find A inverse and multiply it by B, and then you're done. For 2 by 2 matrices, finding A inverse is fairly easy, though we won't be able to avoid fractions here. If A has entries A, B, C, D, that will mean A inverse. Well, it has certain entries, and it's most convenient to write those entries with a number out in front. 1 over A times D minus B times C, which is the determinant of A. And then for the entries in the matrix here, see if I get this right, you got to switch around the A and the D, put the D up here and the A down there, and put negative signs in front of the B and the C. For our matrix here, A is 2, B is 3, C is 3, and D is -5. So for our matrix, A inverse is 1 over A times D, 2 times -5 is -10, minus B times C, minus 3 times 3 is -9. Swap the A and the D on the main diagonal from upper left to lower right. So put a -5 up here and a 2 down there. And put negative signs in front of those 3's. -3 here and -3 there. If one of those numbers, the B or the C, in this spot or this spot were negative, then when I put it down here, it becomes positive, right? Negative of a negative is positive. This is -1/19. Multiply that through. If I've not made a mistake, you're going to get 5/19, 3/19, 3/19, and -2/19. Look good to people? Did you get that? There's A inverse. Now use it. How? Multiply it by B with A inverse on the left, right? So our solution vector is A inverse times B, 5/19, 3/19, 3/19, and -2/19 times the B, that's the constant vector from the right-hand side numbers, -5, 6. You could do this with the definition of matrix multiplication, write a linear combination of these two column vectors with these numbers as the weights. You can also use the slight shortcut of doing dot products. Take the dot product of this row vector with this column vector, and that'll be the first entry of the vector here. And then the dot product of the second row with this column vector. So we get -25/19, 5/19 times -5, plus 18/19, 3/19 times 6. And then for the second component, -15/19 and -12/19. Simplify, it looks like -7/19 and -27/19. Look right? There's the answer. Those are the values of X and Y. I mean, if you wanted to just say X is -7/19 and Y is -27/19, that's fine too. You could also write the answer as a point. X, Y equals -7/19, -27/19. You could graph it. You could graph these two lines. You could see that they intersect at this point. Why do all this if it's a lot easier just to do row reduction, or if nothing else, just, solve one equation for y in terms of x and plug it into the other one? That's a lot quicker, isn't it? Well, okay, first thing I'll say is this method, once you know it, is not that much slower once you know it. That's the first thing I'll say. Second thing I'll say is this idea of using inverse matrices does generalize to other situations, using inverse functions in general that are not necessarily matrices. In fact, the last couple of weeks of the semester, we talk about a very important topic that's different from everything else the rest of the semester. It's called Laplace transforms. And with Laplace transforms, we're going to solve certain kinds of differential equations, and certain kinds of differential equations that you really can't solve any other way, very easily at least, are solved, well, not super easily by Laplace transforms, but it's probably the best method. And using Laplace transforms, you also have to use what are called inverse Laplace transforms. You essentially have to do this kind of thing, except it's in a different situation. It's not with matrices and vectors, it's with functions and actually integrals. But it's the same big idea of using an inverse function. So it's a theme, it's a theme for the course, it's a concept that applies in other situations. It applies for nonlinear systems of equations as well, at least in certain circumstances, not just linear systems. Can I clarify anything?
So your justification for how it works is basically because A times the inverse of itself gives you that linear vector.
Yeah.
Which is theoretically multiplying x, y, x, 1.
Yep.
Because we multiply that side by the inverse by the other side.
Yeah, it's analogous. It's a matrix vector analogy to solving an equation like 5x equals 10 by dividing both sides by 5, meaning multiply both sides by the multiplicative inverse of 5 to get x equals 2, right? There's a very simple linear equation in one variable using just numbers, not matrices and vectors. But this is completely analogous to that, except it's using matrices and vectors. That's an abstract justification for why this works. I also reminded you of the definition of matrix multiplication to justify saying why we can write this system of linear equations in the form ax plus b. That's what I've got here, ax equaling b. Okay. I don't really emphasize this enough in the lectures. It was an oversight by my part. I was so focused on other stuff, I forgot to emphasize this. It's in the reading. Emphasize more. I think maybe I mentioned it once in one of the vector lectures. I forgot which one. I don't emphasize it enough that you can solve linear systems like this. And it does generalize to 3x3 and 4x4 and 5x5 linear systems, although finding A inverse once you get past 2x2 becomes burdensome. Even for a computer, once you get past 5x5 or 6x6. Finding an inverse matrix in general is very computationally intensive. Here's a thought for your future. There's a subject called numerical linear algebra, which is coming up with algorithms for solving very large dimensional systems, like systems 1,000 by 1,000, say 1,000 linear equations and 1,000 unknowns. They do come up in real life applications, industrial applications. Very computationally intensive if you try to do it this way. There are tricks that save computation time. And that's a big subject in numerical linear algebra. Right? So if you go to grad school and you have to solve humongous systems of linear equations, you'll probably be learning about that kind of thing. But you still have to understand these concepts.